So in today's lesson, we're going to take a look at the equations of an ellipse. And you already did this, but we're going to take a little bit of a deeper look into the equation. So in this example, we want to find the coordinates for the center, both of the vertices, and both of the foci. So we have this equation 9x squared plus 4y squared plus 36x minus 8y plus 4 equals 0. So in order to find the center, the vertices, the foci, we're definitely going to want to change this into standard form. Now before we do that, I just want to go over a few things, and you might want to pause the screen so that you can write these things down in your notes. So we need to understand some of the vocabulary that we're going to use, or really more like the variables. All right, so let's take a look at the standard form equations just to refresh our minds a little bit. First of all, we know that an ellipse has two variations, and that's because an ellipse can be oriented in two different ways. So when an ellipse is longer horizontally, we have this equation, x minus h squared all over a squared plus y minus k squared all over b squared, and we know that it always equals 1. Now, when an ellipse is elongated vertically up and down, we see an equation that's been changed. And the change comes in the denominator. Now, this is really important to know because next we're going to be talking about hyperbolas. And there are a lot of similarities between ellipses and hyperbolas, but there are a few differences that really make a big difference. Okay, so keep in mind that in ellipses, the denominator is what's changing. So when we have a vertical ellipse, we still have x minus h squared in the numerator, but now we have over b squared. And then we have plus y minus k squared over a squared still equal to 1. And this makes sense because remember that a, no matter where it is, whether it's here or here, has to be the larger value. And you can think of that as being the longer distance. And so it would make sense, for example, in the first equation, that a, the longer distance, is under the x because we have an ellipse that is long along the x-axis. So that makes it long horizontally. And then we have in the second equation a under y, which makes a lot of sense because we have an ellipse that is long along the y-axis. Okay, so it does make a lot of sense. Now, a couple things. We already know that HK represents our center. And by now you guys know that H and K are always opposite signs of what you see in the equation. Okay. Now we have talked about A and B, but we haven't talked so much about C. And we haven't talked about A and B in the way that we're about to. So A is equal to the distance from the center. So let me show you what I mean. All right, so take a look here. This is the center. All right, and A is going to be the distance from the center to the vertex, or to the vertices. Now, the vertices only exist along the major axis. That has to be the longer one. So these points right here are considered the vertices. So if we take each distance from the center to each vertex, that is called A. And so we can do the same thing on the left from the center to the other vertex, that is also A. All right. Now, when we talk about B, that is the distance from the center to the co-vertex. And we haven't really talked about the co-vertex, but you can probably imagine, you can probably figure out what it is. It's the other vertex, but it lies on the minor axis. So it's these right here. It's the smaller ones, right? So if I measure the distance from the center to each of those are each B values. Okay, so those, I really shouldn't say vertices, but those smaller vertices, which are technically called co-vertices, you can imagine why they're called co-vertices, right? It's to differentiate that they're the smaller one. And those are always going to be along the minor axis, okay? And then we have C. C is going to be the distance from the center to the focus. Now, when we graph an ellipse, we don't generally graph the focus. All right, it's not actually even necessary to graph it when you have all this other information. Like if you have the center, if you have A and B, there's no need to actually graph the focus because we can graph it otherwise. However, the focus does have some really cool things about it, especially when we talk about things like orbits in space, which we're actually going to look at a little bit. There are some cool properties, but I want you to know that the focus is always inside an ellipse. And again, this is important to remember because once we start talking about hyperbolas, the foci are actually going to be outside of the shape. So in in an ellipse, the focus is always inside. So I'm just going to pretend that I actually know where the focus is, and I'm going to say on this ellipse that they're right here. They should be on both sides. It should be equal distance from the center. That doesn't mean they have to be exactly halfway, but they should be the equal distance. So from the center to this foci that I just made up, those values, each of those distances would be considered the C value. Okay, now let's take a look over here because this brings it all together. So when we want to actually find the coordinates of the foci, we have an equation. All right, so we need the C value. We need to know what's the distance of the foci from the center. Because if we have the coordinate for the center, we can find the coordinate for the foci if we just know how far away it is from the center. So we have C as the representing that distance. And so there's a formula, and it almost looks like the Pythagorean identity, or the Pythagorean theorem, right? The Pythagorean theorem says a squared plus b squared equals c squared. Now this is a little bit different. This is a squared minus b squared, all right? So even though it looks really similar, I don't want you to do the math the wrong way by adding. It is required to subtract here, okay? So what we would do is we would plug in all of our values for A and B, because those are probably the ones that we have, and that would allow us to figure out C squared and eventually just C. So you would have to do some square rooting so that you could actually figure out just what C is instead of C squared. Okay, so let's go back to the previous problem and let's actually do the work here. All right, so first of all, before we can ever even start finding the center, the vertices, and the foci, we need to put this into standard form. So we're going to group the x's and the y's. Now you guys did this yesterday, so we're going to do it again. So I'm going to go ahead and rewrite this already in the order that I want it to be in. So 9x squared plus 36x plus 4y squared minus 8y, and I'm just going to immediately move that plus 4 over to the right by doing minus 4. So I'm going to get equals minus 4. Okay, so the reason that I reordered it is because we want to group the x's and then we want to group the y's. So for this reason right here is why I rearranged it. So let's go ahead and actually start completing the square. That's part of the process in finding standard form. Now, before I can complete the square, I have to make sure that the coefficient of my x or y squared term is 1. Completing the square doesn't work well when you have another coefficient. So I'm going to factor out this 9. And when I do that, I'm going to be left with x squared plus 4x. And I'm going to do plus and leave a space because I know I need to complete the square there. All right, I'm going to bring down that plus. Now my second set of parentheses also happens to have a coefficient in front of the squared term. So I need to factor it out. So I'm going to do 4, and then I'm going to be left with y squared minus 2y. And it's always plus. Now why is it always plus? Well, whether the b term is positive or negative, when you square it, remember that the formula for completing the square is b divided by 2 squared. Anything squared is always going to be positive. That's why I keep putting a plus there. I know it's going to end up positive. All right, equals negative 4. Okay, so let's do the math now. So if I use my formula, I'll just remind you, it's b over 2 squared. All right, in the first set of parentheses, my b value is 4, so 4 divided by 2 is 2, and 2 squared is 4. So I'm going to write a 4 here, but remember that whatever I add to the left side, I also have to add to the right side. Now this gets a bit more complex because although I wrote down a 4, if I redistributed this 9, that 4 would not stay a 4, right? And we have to realize that, we have to realize that that value is not just a 4. That value is actually holding a value of 36, which is 9 times 4. So I'm going to add 36 to the right side, okay? I remember that I only factored out that 9 so that it would be easier for me to complete the square. And yeah. So now let's go ahead and do the second part. If I look at b in the second parentheses, it's -2. Well, -2 divided by 2 is -1. And -1 squared is +1. So whatever I add, whatever value I add to the left side, I must add to the right side. And again, remember that this is not just a 1, this is actually a 4 times a 1. So I'm going to add 4. All right, now let's keep going. Let's actually factor this. So I'm going to keep my 9 outside. And when I factor this, I'll do it in some smaller steps, but eventually you really don't have to do it like this. But when I factor this trinomial, I know I'm going to have x and x, and I need to think about, well, what are two numbers that multiply to 4 but add to 4? Right? So they multiply to this number right here, but add to this number right here. And of course, it's going to be +2 and +2. And notice that we have two identical parentheses, which is not a coincidence. We completed the square. We made this a perfect square trinomial. If you remember that vocabulary, it's when we have two identical parentheses. And we did that on purpose. If we got anything other than two identical parentheses, that would raise some questions. We would definitely have done the completing the square process incorrectly. So it makes sense that it's working out that way. Now in the second parentheses, same idea. When I factor that trinomial, I'm going to do y and y. What are two numbers that multiply to +1 but add up to -2? Well, that's -1 and -1. And again, notice that we have two identical parentheses. Excuse me. All right, so we can go ahead and do a little bit of math here. I know these 4s will cancel out, so I'm just left with 36. So what I actually want to do is I want to write down this in simplified form. So I have 9x + 2 squared plus 4 and y - 1 squared equals 36. Now one more thing that we need to do, remember that an equation for an ellipse always has to equal 1. So I need to divide everything by 36 so that my right side actually equals 1. Okay, so when I do that, I'm going to have to simplify this fraction, 9 over 36, which becomes 1 over 4. So essentially I have just x + 2 squared over 4. And then I need to simplify this right here, which will simplify to 1 over 9. So that's just y - 1 squared over 9. And then 36 divided by 36 is 1. All right, so one more thing that we want to do, we want to figure out what a and b are. So I'm going to rewrite these denominators. Instead of 4 and 9, I'm going to have 2 squared and 3 squared. All right, so now I'm going to go ahead and start finding some of these things. So we have hk. So hk, that's the center. So my h is this right here, and my k is this, but remember that I need to do the opposite sign. So this is going to be a -2 and a +1. All right, now what I like to do is I like to figure out what a, b, and c all equal, and that will help me find the vertices and the foci. So a is always the bigger value, okay? So in this case, it's 3. B is the smaller one, so in this case it would be 2. And C I need to figure out. Now remember, we have a formula for C. So C squared equals A squared minus B squared. All right, so I'm going to go ahead and write down that formula because we're going to use it. So c squared equals a squared minus b squared. So I'm going to plug in some of these values. So a squared, 3 squared is 9, minus b squared, which is 4. So I get c squared equals 5. And so if I square root both sides, I would get that c is equal to plus or minus the square root of 5. I can't simplify that radical, so I'm just going to leave it that way. All right, now, since we're talking about a distance, we can just really leave it as a positive. So I'm just going to write this as square root of 5. Now, we're not done, though, because we need to find coordinates. The only coordinate we've found so far is the center. So let's go ahead and find the coordinates for the vertices. Now remember that the vertices are on the major axis, so I need to know the orientation of this ellipse, and I don't even necessarily need to graph it, but if it helps, you can just give yourself a picture. All right, now since a, the larger value, is under y, I know that this ellipse is long vertically, okay? So I'm looking for the vertices, which would have to be these 2 points. Okay, so from the center, I could have drawn this a little bit more accurate because I know the center is negative 2, 1. I just didn't. But the change is happening in the y coordinate. All right, x is not changing. Y is the value that's changing because the vertices are moving up and down the y direction. So what I want to do is I want to add a to my y coordinate. So if I take a look at my center, right, which is, let me just erase some of this so that I have a little bit more space. All right, what I'm going to have to do is my x value will stay, but my y value, I'm going to have to add and then subtract the a value, which is 3. So I can't just leave it like that, though. I need to actually do the math. So this is going to be negative 2, comma, well, 1 plus 3 is 4. And then I have another vertex, so that's negative 2, comma, 1 minus 3. 1 minus 3 is negative 2. And these are the coordinates for both of the vertices. Now for the foci, same idea. The foci also lie along the y-axis in this case because the ellipse is long vertically. So I'm going to start with my center, negative 2, 1, and again I'm going to add and then subtract because I need to go in 2 directions. I need to go up and then I need to go down, and I'm going to add and subtract my c value, which is radical 5. Now in this case, actually, I can just leave it like that, and I'm going to tell you why. When I actually write out these 2 coordinates, negative 2, comma, 1 plus radical 5, I cannot actually write 1 plus radical 5 any more simplified than it already is. And the reason is that I want to keep it exact, right? I could actually plug in to the calculator 1 plus radical 5, and I would get some decimal. But remember, we always want to be exact. Because 1 and radical 5 are not like terms, because 1 is an integer and radical 5 is a radical, they can't be added, right? So I can only write it as 1 plus radical 5. And then the other coordinate would just be negative 2, comma, 1 minus radical 5. So you can see that in the end, we could have actually just said negative 2, comma, 1 plus minus radical 5, and that would have been a really shorthand way of writing both of those. But if you like to see the 2 equations, the 2 coordinates, you can certainly write them out that way. Now, if the foci, if c was actually an integer, a whole number, you would actually have to do the math, like the way that we did it in the vertices. You can't leave it as 1 plus minus 3, for example. You can actually do 1 plus 3 and simplify, and you can actually do 1 minus 3 and simplify. So you always have to go as far as you can in simplifying, okay? Now, if any of that was confusing, I would highly recommend going back and rewatching some parts. So some of these things are new, especially the foci. So it's okay if you have to go back that's fine. You might need to do that. So let's talk about something called eccentricity. All right, eccentricity. Eccentricity is actually pretty cool. It's a number that represents how oval or how circly, that's a very unmathy definition, uh, a shape is. Okay, so this is awesome. I love this. I'll just read it because it's better if I just read it than try to re-explain exactly what you see on the screen. So when one of the reasons that it was difficult for early astronomers to detect that the orbits of the planets are ellipses, so if you didn't already know, I'm sure you do, but the planetary orbits are ellipses. So the reason that it was difficult for them to realize this or to detect it, like to find that out, is that the foci of these elliptical orbits were super close to their centers. So it was almost unidentifiable. And so they believed that there was no focus because they were so close to the center that they couldn't even differentiate it. So they believed that the orbits were pretty circular. Later on, we find out that they're not actually circular, that they are elliptical, and you know from seeing pictures and studying this in other classes that the more with better technology, obviously, we can clearly see that these orbits are elliptical. So this idea of eccentricity comes into play. It's a number that measures how oval an ellipse is, and some ellipses can look almost perfectly circular, but they are technically not. Okay, so this is a cool concept because it really gives us a good idea of how our planets orbit, which is important. So eccentricity is a very simple formula. All right, it's E equals C over A. And we just saw how to find A, B, and C. So when we find eccentricity, E, we just have to take C and divide it by A. And this number will be a decimal, all right? So our eccentricity values for an ellipse are always going to be between 0 and 1. They will never be less than 0, and they will never be more than 1. This is going to change when we talk about hyperbolas, but right now we're talking about ellipses. So if an ellipse is almost perfectly circular, that means that the foci are super, super close to the center. And because of that, when we do C divided by A, we get a number that's really, really close to 0. Okay? So the closer you are to 0, the more circular your ellipse looks. All right? And then on the other hand, if your foci are close to the vertices, so they're really far from the center, when you do C divided by A, remember A is actually the distance from the center to the vertex. So if C and A are almost the same, then you're going to have a number that's really close to 1. And the closer you are to 1, the longer, the more elongated your ellipse will be. Okay? So here are a couple pictures to help us see that. So here is the center. Notice how close the foci are. And notice how, and this is an accurate representation, notice how circular this shape actually looks. But it's technically not a circle. All right, I know it looks super like a circle, but it's technically not. All right, and then on the other hand, we have a center here with foci that are pretty far from the center and actually really close to the vertices. And in that case, you can see that when you do C divided by A, you're going to have something really close to 1, and this ellipse is much more elongated. Okay, so I want to go ahead and find eccentricity for the example that we just did. So I'm going to go back a little bit. You guys can go back to that same example. We're going to add one more part. We are going to find eccentricity. E equals C divided by A. So all I need to do is plug in my C value, radical 5, plug in my A value, All right, and now I'm just going to get my calculator and I'm going to do radical 5 divided by 3 and I'm going to get that decimal and I get E equals 0.745. I'm going to do 4 decimal points. It's 74535. So that's going to round that up to 4. So I'm going to say approximately. Okay. So because that number is closer to 1 than it is to 0, I know that this ellipse is pretty elongated. Okay, so the picture that I have here maybe is not so inaccurate as far as how elongated it is. All right, it definitely is inaccurate as far as the center. I could have definitely done a better job with that, but that was just a quick sketch. All right, so this is the focus of today, no pun intended. We are looking at the center, the vertices, the foci, but now also this idea of eccentricity. So you guys are going to work on some equations where they're given to you just like this, and you need to dig out the information to find out what the center is, what the vertices are, what the foci are, and also what the eccentricity is. All right. So once again, if you struggled with any of these concepts, I really encourage you to just go back, rewatch some clips, ask your classmates, work together, and I should be back with you on Monday. So I will certainly answer questions that you have, and feel free to email me as well.